Hi, thanks you all for coming to my talk. I'm the first author CHI'20. The work I'm presenting today is a preliminary study of messaging notifications in virtual reality. This work is conducted from the MUI lab in National CHI'20 University, and my advisor is Professor Yongwu Zhang. In recent years, a variety of immersive virtual reality applications have been developed and popularized. These VR applications provide their users with diverse experience in immersive virtual environments. By their nature, this immersive experience can result in users losing connectedness with the real world. For example, they may lose their awareness of incoming calls or text messages. However, VR users may desire to be notified about real-world events, such as their friends' messages. In this case, they may want to check the notifications directly in VR, rather than take off the head-mounted display. So the question is, if we want to present notifications in VR, how should we do that? According to previous interruption research, finding the optimal moment and way to present notifications is very important, as we want to let users notice the notifications while minimizing the disruption. There have been some studies exploring different presentations of notifications in VR. However, the challenge is that people may conduct different applications in VR. But those existing studies did not explore how users' receptivity of real-world notifications will be affected by specific kinds of presentation in different kinds of VR applications. So we conducted an experiment using 3 notification displays to send notifications in 4 VR activities. The 4 VR activities we designed varied in 2 dimensions, whether it is time sensitive and whether it requires visual attention. The first VR activity is watching a 360 video, which is time sensitive and might occasionally take over a user's visual attention. The second one is playing a rhythm game. In this game, participants needed to wave their sword to hit the target in order to earn points, and there is vibrating feedback when the correct target is hit. This activity was highly time sensitive and required constant visual attention. The third one is playing a treasure hunt. In this game, participants needed to find 3 hidden objects by walking around an office. Because they had to keep looking for hidden objects, it required some level of visual attention. However, the game had no time limit, so it was not time sensitive. The last one is waiting for system loading. While in loading, participants were just waiting for the next VR application, so it was not time sensitive and did not require much visual attention. We then designed 3 notification displays inspired by prior research and common VR applications. The first one is the HMD, which was fixed to the upper left corner in the user's field of view. The second one is the controller display. It shows notifications on a pad attached to the controller like on a smartwatch. The last one is the movable panel display. Our design consists of a transparent black panel that showed notifications, and users could move it to anywhere they preferred at any time. To make it easier for users to notice the notification, we added vibration feedback to the controller when they received a notification. So our research questions were: Question 1. In which VR activities do users perceive notifications as the most disruptive and have the worst recall of them? Question 2. Which notification displays are more suited to presenting notifications across various VR activities? So in order to answer these research questions, we conducted a within-subject experiment examining the effect of 4 VR activities and 3 notification displays on users' perceived disruptiveness, perceived timeliness, and recall. We recruited 40 participants aged from 20 to 27. Most of them had some experience with VR. Only 5 participants were new to the whole VR experience. This is our study procedure. Each participant played 3 rounds, and for each round, they used 1 type of notification display. In each round, participants experienced 3 VR activities, and before each VR activity was the loading. The order of the notification displays and VR activities were randomized and counterbalanced. In each VR activity, participants received 3 notifications. Each notification was sent randomly within a 20 seconds time window. Each time window was separated by a 45 seconds interval. In the loading activity, participants also received 1 notification. We used instant messages as notifications in the experiment. The notification lasted 12 seconds, and to make it more realistic, we also diversified the content, senders, and scenarios of the messages. After each VR activity, participants answered a post-test questionnaire that contained 4 sections. Simulator Sickness Questionnaire, a recall test regarding messages, perception of each message including disruptiveness and timeliness, and the participants' level of engagement in the activity. Now, let's move on to the result of our investigation. In terms of engagement level, we found that participants were the most engaged in Reason Game, followed by Treasure Hunt and 360 video and loading. This suggests that when an activity is time-sensitive or requires high visual attention, people tend to feel more engaged. Our research questions indicated that we were interested in knowing the perceived disruptiveness of notifications in different VR activities. And we found that participants perceived the highest amount of disruption during Reason Game, followed by Treasure Hunt, 360 video, and finally, loading. Similarly, participants perceived the Reason Game to be the worst time to receive notifications. These 2 patterns seem quite consistent with the engagement that we saw earlier. It seems like the more engaged participants were in the VR activity, the more disruptive and ill-timed they perceived notifications to be. In particular, participants thought the control display was the most disruptive in the 360 video and was the worst time in Reason Game. According to our quantitative analysis, the participants feel that while watching 360 videos, seeing the notifications on the control display requires additional effort. For example, P31 said, "The best thing about control display is you need to move it. When the time is urgent to read a message, you may not be able to read it so quickly." Another reason why participants perceive notifications using control display in the Reason Game to be the worst time was because it often blocked the viewing content and did not allow the users to see the notifications clearly when the control was moving. As P18 said, "I can't really choose to place the controller wherever I wanted in a Reason Game. I can't flexibly adjust the position of the notification." In addition to perception of notifications, whether people remember the notification later is also important. So we were also interested in the recall of notifications. We found that in general, participants had the worst recall of notifications after playing the Reason Game. However, participants could still recall notifications quite well when using HMD. According to the quantitative findings, it was because they found the HMD easier for accessing notifications because it was in a fixed location. As P39 said, "Since HMD is right in front of me, I can determine whether the text is important or not just with one glance in the middle of a task." Also, some participants relied on vibration to know whether the notifications come or not. However, the Reason Game also used vibration as a signal when the user hit the target. So the ambiguity of vibration purpose led some participants which using non-fixed location display to not easily aware such notifications. On the other hand, when using the movable panel display, participants also had worse recall of notifications in time-sensitive content like 360 video and Reason Game. This was because some participants found it troublesome to place the movable panel display in a good position, and would rather not do that when content is time-sensitive, which makes it harder for them to notice the notification. For example, P33 noticed that when movable panel is in a bad position, I don't have enough time to move it back. In another example, P19 said, "Since the video will continue to play, I might miss some content if I choose to read the notifications. Now let's discuss the result. To summarize, we found that the more engaged the participants were in a VR activity, the more disruptive and ill-timed they perceived notifications to be. However, we found the most interesting was there seemed to be an interplay between the time sensitiveness of the content and the characteristics of the notification display. For example, when content is time sensitive, users don't have enough time to move the movable panel display if it is in a bad position. And the control display also requires additional effort lifting your hand to see notifications, and this action may also block the user's viewing area. As for HMD, due to its accessible, it has an advantage that allows users had a better recall of notifications when the content is time sensitive. Our result implies that the key factors in the perceived suitability of notification delivery methods were: first, the time sensitiveness of the VR content. Second, the location of the display. Third, the need to physically move to see notifications. And fourth, the use of the same modalities for messaging notifications and VR content. Based on these findings, we argue that future notification systems on VR platforms should be attention-aware, content-aware, and modality-aware. The VR platform should be attention-aware. When users are highly engaged in a VR activity, the VR platform should not inform them of notifications unless they are deemed important. The system could use some features like eye-tracking data to detect users' engagement levels and determine breakpoints to deliver notifications. The VR platform should be content-aware. When content is time-sensitive, it should display notifications at a fixed location, without requiring users to do more actions to see them. This will help ensure that they do not feel forced to decide between enjoying VR content and responding to real-world events. Additionally, we believe that VR platform could adopt a more technical approach, such as computer vision, to detect the region of interest dynamically and adjust the location of notifications so that it does not block the major content. The VR platform should be modality aware. The notification systems should distinguish clearly among modalities so that they can avoid the confusion caused by using the same modality. The platform could inform the user with options, including other modalities, or create a standalone wearable device, such as a ring, for sending haptic notifications. A more detailed design guideline was discussed in our paper. In conclusion, we presented a study that investigated how to present real-world notifications in different VR activities. We found that while engagement level was an important factor in whether users wanted to be notified, the time sensitiveness of VR content, the location of the display, the need to move the display to see notifications, and use of the same modality for messaging notifications and VR content also influenced the perceived suitability of a specific notification display type. However, we freely concede that our current study is only a start, and we will need further investigation for the design space of notification systems in VR. Thank you for your time.